Hello again, it's your friendly heavy physics teacher here with my college physics lesson, Unit 9, Lesson 6 on electromagnetic induction. Yes, I know that it seems like I've jumped a couple of lessons, but we're going to move forward with this uh, so that you can see this. Today we're going to be talking about how we use electromagnetic induction to generate electricity as opposed to using electromagnetic induction to convert electricity into a mechanical force. All right? And unlike static electricity, this isn't quite as shocking, shall we say. All right. Before I get to the particulars of how we're going to calculate all of this, a little demonstration to show you what I'm talking about. All right, here we have a galvanometer. Hopefully this time you're going to be able to read the meter as things happen. I realized that when I did this with my other demos, you actually couldn't see the ammeter that I was talking about. Got a magnet and a coil of wire. It has about 50 wraps of wire around it. Okay, the wire is enameled so that when each one is in contact with the other, it's not conducting in between them. So the current has to go around and around and around and around through, okay, if there's current flowing. All right, so I'm going to turn this sideways so that we can see what's going on. All right, so right here, magnet, wire, and notice if I move the magnet, look at the deflection that's over here. Notice I get a small amount of deflection. Now, this device is purpose-built to measure the presence of electric current. What's happening here is I'm creating a voltage in the wires, and because that voltage can be used by this, it can be detected by this, that voltage is going to let a current flow in the wires, and that current is measured by that deflection. All right? So I have a north pole, and it's going one way. Notice that if I switch the motion, it switches the direction of the current. Flip the bar magnet around. Now I have the south pole going in. Oh, notice that the deflection is opposite to the way the north pole was. So there obviously direction of motion and direction of the magnetic field has an effect here. Also, notice that I can move the wire and produce a similar effect when I use, instead of moving the magnet. So it really doesn't matter if I use the motion of the wire or the motion of the magnet. In either case, I'm generating electricity. And that's the principle on which the electromagnetic induction works for generating electricity. Prior to this, we talked about it in terms of generating a mechanical force on the wire. If I were to have this wire in a magnetic field, let's say I had a north pole here and a south pole here, and this produced its own magnetic field, well, then we'd see this moving in some fashion in that magnetic field, okay? And so it might move up, might move down, might move to the side, depending on the orientation of the magnetic field. Here we're doing just the opposite. We're taking mechanical motion and turning it into electricity. Okay, so how much electricity are we actually getting? All right, so this equation here represents the interaction of the magnetic field and how quickly that interaction is taking place. All right, now this script E stands for EMF. EMF, Electro-Motive Force. That is the archaic term for voltage. All right, back in the 1700s, back in the 1800s, they didn't talk about energy. It hadn't really been defined yet. Okay, there was this huge discussion during the late 1700s, early 1800s is actually an argument between the European scientific community and the British scientific community about how they were going to define what energy actually was. They talked about it. Heat was energy and things like that. But they weren't really had a definitive definition. It wasn't until the middle of the 1800s that it really started being defined as we use it today. So they were always talking about the interaction of things as if they were some kind of force. Okay, well, the electrical force that was causing current to flow, that was creating pressure, they called the electromotive force. All right, it's not a force. All right, it is actually voltage. It's a potential difference. Okay, so we use this script E to represent EMF. Greek letter phi stands for the magnetic flux. Flux is a word that means change. Flux is how an interaction is happening to create a change to happen. Okay, so the change in flux divided by how much time it takes that change to happen is equal to the EMF. Now, on your reference table, you notice that there's a negative sign here, okay? Because a positive potential difference is created when you have a negative change happening over here. In other words, if the interaction gets smaller, you're going to produce a positive EMF. If the interaction gets bigger, you're going to produce a negative EMF. All right, it's the way we determine which way the current will flow. Okay, so EMF equals the change in flux divided by how much time it takes that change to occur. All right, so what do we mean by magnetic flux? What is this interaction that is taking place that can change? Okay, magnetic flux is the interaction of a magnetic field with an exposed area of a conducting medium. All right. What that means is I'll get to in a little moment. All right. So the magnetic flux, phi, is equal to the magnetic field intensity times the area that's exposed. Now, notice I've got my vector symbols here. This is a vector dot product. So what this means is it's the direction of the magnetic field in addition to the amount of the magnetic field times dot the direction of the area times the actual amount of area, the magnitude of the area. What? There's direction to area? Okay, this is something you're going to have to ask your math teachers to help you define. What we mean by the vector that represents the area is that, okay, let's say my board is my area that I'm concerned with here, the whiteboard. The vector for this area, the vector that defines the direction that this area is exposed to, is perpendicular to it. In other words, the A vector for this board would be coming out toward you. That would be its positive direction. The negative direction would be back toward me. All right? So vector B times vector A, the magnetic field intensity vector, times the face area vector produces the magnetic flux. Okay? So since it's a dot product, phi equals BA cosine theta. For just about all of the incidences that we're going to ask you to look at, the area is going to be acting parallel. The area vector is going to be acting parallel to the exposed magnetic field. And so cosine of 0 degrees is 1. So simply multiply the two together. All right. But understanding this, if all of a sudden this were to turn this way and my magnetic field were going into and out of the picture here, but now the vector for the board is is going that way, and since they're perpendicular to each other, we would get no magnetic flux if that were the situation, okay? So this is what we mean by magnetic flux. Now, what do we mean in actual, real, physical, real life thing terms? Okay, back to my demonstration thing here. That right there is the area of the conducting medium that is exposed to a magnetic field. All right, so in this case, we go, pi r squared, all right, would be my area. The vector for this is either into or out of this area, all right? So if I were to use a pencil, okay, the pencil point is pointing in the direction of the area vector for this coil of wire, okay? All right, magnetic field, all right? The direction that this magnetic field acts relative to the area of wire exposed determines how much flux is happening, all right? So this magnet has a magnetic field intensity of probably 0.01 Tesla. It's really small, okay? Compared to the Earth's magnetic field, that's actually quite large, all right? So notice that by moving the magnet into the wire, I get a certain change there, okay? Notice if I do it quickly, I get a bigger change. Aha. So the B times the A didn't change, but the delta T did. All right. So there is a change here. This B is low right now. And as it goes through, it's high and then it's low again. Notice that each time I'm moving this, yeah, there's a little bit of deflection over there. All right. Now, watch what happens when I use 2. Okay. What happens if I use 4 of them? Having trouble holding them together. Okay. Notice that I get a really, really big deflection now. Okay. What if I change the area that's exposed? Now, I could use a bigger diameter here. All right. But then I'd also have to use somewhat larger magnet, same magnetic field intensity, but somewhat larger magnet to fill that area. What if instead I put another loop of wire? Does that increase the area of conducting material exposed to it? Think about it. If I did just one wire here, do you think the deflection over here would even be noticeable? So notice I got a whole bunch of turns of wire on this. Okay, like I said, there's about 50 turns of wire. And so that's 50 times the area of one loop that's exposed. Okay. Let me use a different loop. And I had to put masking tape on this because I put 4 times the amount of wire on this that I did for the other one. Okay, there's like 200 turns of wire on this compared to 50 for that one. Okay, so here we go. A single magnet. Not quite the same as having 4 magnets through it, but notice it's a lot more than the single magnet with this loop of wire. Okay, let's look at it with 4 magnets and see how that changes things. Huge deflection. Okay, now remember, it doesn't just have to be the magnet that moves. It can be the compass that moves. Okay, or not the compass, the coil that moves. All right, so magnetic flux, B times A, B times A. If there is any relative change between these, okay, so right now no change is happening. Oh, the magnetic flux is interacting with the coil, but because there's no relative change between them, no EMF is being generated. Boom. Change happened. Now it produces an EMF. Change happened. Now it produces an EMF. Okay? So, there we have it. Electromagnetic induction from the standpoint of generating electricity. Okay? The interaction of the magnetism with the area exposed determines the voltage that will be generated. Connect that to a load, and then you get a current flow. Okay? So that voltage divided by the load that it's on determines how much current will actually flow. Alrighty? So there we have it. Electromagnetic induction for generating electricity. Please be on the lookout for my emails. Now that you've seen this, you can do the PhET lab that is examining or investigating electromagnetic induction. Okay, that lab will make more sense now that we've done this. I will see you during our next online meeting with questions about the lab and the worksheets that I've sent out. Hopefully in this time of COVID-19, we'll get through this, and hopefully you're all staying healthy, and I'll see you soon back at school. Bye-bye now.